All right. Good morning. Thank you for coming to the talk. My name is Yiling, and it's a great pleasure to present our work, machine learning aided peer prediction here at EC. This is a joint work with Yiling. She sits there. So I'm going to talk about machine learning and peer prediction as a connection between these two. So let me start with this general background about peer prediction. So our discussion or our motivation starts with this very classical question about information elicitation without verification. So consider a scenario, we as a principal or as a designer, we want to elicit private opinions from set of agents. So these opinions are private. It could be some private opinions about some political issues or political events, or it could be some private information about some survey questions. Or more recently, in this data collection for machine learning, this private information could be people's perception about the ground truth label, right? And the goal of this principle is to read agents' minds, to collect these truthful reports from the agents, but you don't have verification. This problem is challenging when it's costly or even impossible to verify the reports against this observable ground truth. Like consider the case, if we are getting peer grading from students, let each other grade each other's homework, then it's going to be really costly for us to further verify the quality of the gradings, right? And since people start to realize this question, there's a very nice theoretical idea called peer prediction that has been proposed. So it's actually very simple. Jointly, under some assumptions, peer prediction refers to a family of mechanisms that can truthfully elicit private signals at equilibrium. So that means if I'm an agent and if I believe everybody else is truthfully revealing their private opinion, it's also my best action to do so. The idea is also very elegant. Since you don't have ground truth, you just send each question to two people instead of one. And you're going to use these two copies of answer to cross-validate or cross-verify each other. And then you're going to design a payment table, or what we call reward, to reward each agent based on how well each report predicts another. Right? These rewards can be realized using reputations, scores, coupons, or even money. You just issue people some money to cover this score. And they're going to achieve a truthful equilibrium by carefully designing this mechanism. With all this goodness, certainly peer prediction has drawbacks. So first of all, this elicitation mechanism introduces the redundant assignment because you're sending each task to at least two people to get this redundant copy. So consider this machine learning application. That means your labeling budget is reduced to at most half immediately, right? That remains some concern. The second is like usually this mechanism requires some assumptions on this prior knowledge of agent's observation model, but this also remains largely unknown. And thirdly, many times this peer prediction has this uninformative equilibrium, meaning agents just simply reporting the same answer is going to be equilibrium. It's a very trivial equilibrium, but it's uninformative. We want to avoid this case. So in order to proceed, let me just visualize our information structure and say what peer prediction does and what our mechanism does. So we have this very simple information flow. We have a question. And the question with certain probability has a ground truth answer, being yes or no. So we consider the binary outcome space. And further conditional on the ground truth answer, each agent forms their own personal belief. So it's a noisy copy of the ground truth. We assume this is common knowledge to all participants about this information structure. And what peer prediction does is, let me rephrase this information structure using a more like machine learning type of context. Is we start with some feature vectors that describe our task. Right? This is a feature vector. And there's a ground truth label, or the ground truth answer, coming from this prior probability 50-50. And then the human label is a further a noisy copy of the ground truth label. It's flipped from the true labels. And what you get is actually the report that's the collected label from the agents. Note, it could be different from this observation. So peer prediction, what peer prediction does is essentially utilizing the correlation between these two signals. So how agent's observation correlates with ground truth. And through the ground truth, you can say any two agents' signals are also correlating with each other. Right? And the next step is very simple. You just design a payment function that takes these two reports in as the input arguments, and you leverage this correlation to pay people based on these two reports. So note, I highlight this peer agents reports in a different color because when we look at this methodology, we look at this design philosophy, we found what we really need is just a prediction on the ground truth label Y. So we can have two correlated signals. And in classical peer prediction, this is done by getting another report from another agent. But this is not necessarily the case, right? Because if we want a prediction, machine learning can help us do so. A large part of machine learning is to predict. And secondly, if we go back to the figure, we see the first component is largely ignored. We haven't talked too much about the feature vector. Rather, we utilize the correlation on the signal space. So presumably, this feature vector correlates with ground truth Y. So how do we utilize this correlation? So another dimensional correlations. And machine learning can do this association too. So that's also the basic functionality of machine learning, to associate X with Y. Combine these two bullets, our idea is very simple. We want to leverage the correlation between X, Y, and to use machine learning to do peer prediction. So to realize it, we're going to replace another agents with a machine. Right? So it's more like machine prediction instead of agent prediction. So what are the advantages and what we did in this paper is, first of all, it's budget efficient. We don't need to reassign each data. We train a learning algorithm to make a machine prediction. We also remove the requirement of knowing the agent model. Rather, we're going to show we can learn this agent model from the data. So this may be of independent interest to other studies. And we show our mechanism achieves strictly truthful Bayesian-Nash equilibrium, and an informative strategy is no longer equilibrium. Also, our mechanism is able to induce effort exertion if people are effort sensitive. These are some advantages, but from a higher level, we really want to say we have been knowing this human data has been helping machine learning, but the other direction hasn't been understood that much. So our work is trying to fill in this direction, saying machine learning can actually also help back with incentivizing high quality human data from the agents. So to formalize this challenge, I want to just quickly go through the model. We have n samples, they are IID. The samples xi together with the ground truth yi, I draw from the distribution D. And we have a binary class, it's either plus or minus. And as a mechanism designer knows the prior. So notice this is prior over the ground truth, not the prior over the agent's observations. An agent's observation follows this two-coin flipping error model. That is conditional on the ground truth label. You have a different error rates in terms of making a wrong observation. The presentation will focus on homogeneous workers, but our results largely extend to heterogeneous when people have different error rates. We consider Bayesian informative workers. That means each worker, after their observation, their posterior belief will improve over their prior. And we actually found this is equivalent with saying the two error rates, the sum of two error rates is less than 1. So why I put it here? Because we found it's very interesting. We have been noting this condition consistently in machine learning literature when you do learning with this type of flipping errors, but we haven't found a concrete interpretation of why this is needed. We give sort of like an information type of interpretation why this condition is crucial. Each data is assigned to exactly one worker, so no redundant assignment, except for a small fraction which will be sent to 2. I'll mention this later, why we need it. So with this, I think the challenges are also sort of clear, and I list 3 of them here. The first is how to learn a good prediction from the human-generated data. That's the only data we have. And how to design scoring function to incorporate this machine prediction. And like, you're going to notice the first two steps. In order to do the first two steps, you need to know the noise error rate in the agent's reports. And I'm going to talk about how do you learn the error rates when you even don't have ground truth. So when I was talking with Yiling, we found like learning with human data is essentially equivalent with learning with noisy data. Right? And suppose you have this noisy copies or samples xi, y tilde. How do you learn a good predictor? Directly minimizing the risk doesn't sound right, because if you find a function f that can best explain this data, it's not proper because it's y tilde incorporates noise. It's going to propagate into your learning procedure. So it's not appropriate. So the idea is to define surrogate loss function over the L function to remove bias. So there are several ways of doing this. One simple example is to define surrogate loss function phi as a linear combination of the loss function defined over the noise label plus the loss function over the other label. This term is to account for the fact this noise label may come due to errors. And the linear coefficients are the functions of error rates. And why this particular form? It's actually very simple, because when you take expectation, the surrogate loss function becomes exactly the loss function evaluated as a true label. So in other sense, the surrogate loss function is the unbiased estimator of the true loss. And then you do risk minimization over the surrogate loss function, it's going to converge to the true losses. And when you have enough samples, you're going to have a good training, and you're going to have a good predictor, f tilde. And you plug this f tilde to each data xi, you have a good prediction if you believe your optimal classifier is decent. But note, we need to know the error rates, right, in order to define the surrogate loss function. So secondly, we have this prediction fxi. How do we combine fxi with the reports? So many existing peer prediction mechanism requires actually you know the performance of this prediction. But before we actually deploy the classifier, we don't know its exact performance. So how do we design the scoring function? And very interesting to us, we found there's a very nice connection between the loss function and the scoring function. So we show the surrogate loss function can serve as a scoring function. We just simply pay each worker the negative of the loss function to make it a scoring function, and plug in the prediction fx and the reports yi. And why this gives us a strict truth for Bayer-Nash equilibrium? That's because the intuition is the surrogate loss function is going to remove the bias in agent's reports. So if I choose for report, I know my report is going to appear as if it's a ground truth. And it's positively correlates with the optimal classifier's prediction. Or to realize the proof, we have the scoring function, we have the loss function. So agent's reports correspond to the noisy label, and reference reports correspond to the classifier. So maximizing the reward is equivalent with minimizing the loss. So that's why the loss function can serve as a scoring function. But this, I want to note, this is not the only way to combine these two. We also have another mechanism which is simpler, requires a little bit more, what we call machine output agreement. So after all, the first two steps, defining the surrogate loss function and defining scoring function, both depends on knowing the error rates. So what if we don't know the error rates? And what if we don't have ground truth to learn the error rates? So we ask the question, what statistics are observable that can help us learn the error rates? And we found the following two equations are enough for us. So the first statistic is the probability of matching. So this is the only place we need to reassign some data to two agents, because we need to know the probability of matching. So the probability of matching is we send each data to two agents. We check how often they match each other. And this probability can be written as a function of E plus E minus the error rates. So E squared is the probability both get it wrong, and 1 minus E squared is when they both get it right. And the second equation is simply the fraction of negative labels that we observe from data, and it also can be written as the function of E plus plus E minus. And we show with these two equations, it can accurately learn the error rates when agents adopt symmetric strategies. We have some recent idea of what if people have asymmetric strategies. We can also learn the error rates to some degree. So then you can imagine if you have enough learning, enough samples, you can learn the error rates carefully. And we show with the error rates are small enough, this truthfulness for the clean case will remain. So this is some simulation. You can say when we have more data points, the error rate drops sort of like decently. All right, so I want to leave some time for questions. And before I end this discussion, I want to mention this mechanism gave us a way to formalize this notion of machine learning elicitability. So we call it data distribution being machine learning elicitable if there exists a mechanism that can learn a classifier and a scoring function at the same time, such that it has a strictly truthful reporting equilibrium. And we found actually such data distribution is not that rare. As long as a data distribution is machine learning elicitable, we prove if the following three conditions hold. The first condition saying there's a concept class over the data such that it has a bounded VC dimension. So this is roughly saying it's learnable with a finite number of data. And the second and third conditions are actually simpler. It's simply stating this optimal classifier in this class is going to be better than random guess. That's the only thing we need. If it's worse than random guess or it's equal to random guess, you can learn nothing. Really, you really can learn nothing from this class. So these three conditions are enough or sufficient to give you a machine learning elicitable data distribution. I also want to conclude by saying, so far the results is presented as if we are eliciting the truthful reports, but also the results can be easily extended to a case when agents are effort sensitive, and we can induce effort to improve the quality of the data. With this, I conclude the talk and welcoming questions. Thank you.